Sometimes in our programs, we need to either save the objects that we have in memory, such as storing them in a file or a database, or we need to transmit those objects, like over a network connection. When we store or turn an object into a stream of bytes, this is called serializing the object. And when we restore an object from some stream of bytes, such as a file or something sent over a network connection, this is called deserializing our object. The main difficulty in doing serialization is that objects often have references to other objects. If we need to follow all of those references to make sure that our object is still valid when it's been serialized and deserialized, then as we follow those references, they start to form a graph. Similar to the way that we had to follow references in mark and sweep for garbage collection, this can take a lot of work. And the graph that we get may be large and complex. There may be cycles in it. There may be objects that are repeated throughout it. And so we want to be able to do serialization in smart ways that make this effective and efficient. First, we'll start with some simple examples of serializing. So here we're writing a serial list. We write that it implements the serializable interface. You'll notice we give it a version ID for the serialization that's being done. We'll talk a little more about that later. You'll also notice that its cells are serializable too. This is necessary because any object that our serial list has a reference to needs to also be serializable. So our cells are what our list is made up of. They all need to be serializable if we're going to use some of the built-in options for serialization. The serial list instance only has 32 bytes of data itself, and then all the rest of the data will be in its cells. The 32 bytes being some of the basic object representation and its head and tail and its size. So we have to store that graph of the cells. The last cell, you'll notice, is reachable from two paths. You can get to the last cell by stepping from head to next to next to next until you get to the end. You also can get to it just by using the tail reference. A doubly linked list would be very complicated to do this with because its graph would have cycles. The head would point to its next, and that next would point back to the head. So as we try to follow the references with the default serialization methods, it would just cycle potentially forever there. Here are some of the basic methods for the linked list. You'll notice that they're really just regular linked list methods. So we can add in various circumstances, we can check the size, and we can turn to an array. All things that a regular linked list would do. There's nothing special about these methods. What we will add special is a serialized list method and a deserialized list method. They, you will notice, throw some potential exceptions because they're going to use streams. And they build an output stream, for instance, for serializing. This is sending to a file. As I mentioned before, you don't always have to send to a file, and for your homework in this class, you'll use some other methods for serializing. But here it just sends it to a file output stream. It calls writeObject on the list. This will use the default Java serialization, which we'll see is not the most efficient. But it will get the job done. It will take all of the data from it and follow that graph of references and serialize every object that the list contains or has a reference to. And then we close our output, and we're going to return the length so that we can see how much space was used by our serialization method. And then on the opposite end, when we deserialize, we can then just use the read object method from the input stream, which is built in, and cast it to be a serial list, and then return that after closing the input stream. So this is easy, but we'll see that it's not that efficient. So we use this object output stream, which will create bytes from an object, doing that default serialization, and an object input stream that will create an object from bytes, the default deserialization. The bytes that we get can come from a file or a network socket or lots of other possibilities. Here you can see they're just programmed to come from a file. Your programs may be a little more general and might just ask for any kind of stream and then build an object input or output stream on them, or do things like that rather than specifically a file. So here we have what could go in a main method to do some building of a list and some serializing and deserializing. You can see that we create a file to store our list in, we create an empty list, and then we serialize that empty list to see what the file size is when it's empty, which here it turns out to be 83 bytes. And then we add some things to that list, and we convert it to an array, and we print out all of the things from that list, and we do some comparisons with items from that list. So then when we ask to serialize that list that has things in it, we get a bigger file size, of course, and you'll notice that we ask the thread to sleep, which with this number lets 10 seconds go by before we deserialize the list and put it back to be an actual list object we can work with. Then we turn it to an array, we get all of the items out of it, and print them out. The reason that we had the thread sleep for 10 seconds is because there was a date stored here, and that was the current date and time. And you see that it had 19 seconds as its ending number there. And when we deserialize it, the date and time should be the same because we're reading back in the stored one, not generating a new date or time for that. The first and the third references share the same object, but the second reference is different. You can see here that we added S, and here we added S. Here we asked for a new string, so that will create a new object in memory. So these are actually the same contents, but only two of them have the same reference in memory. A0 is not equal to A1 in terms of memory equality. If we tried to use the serialization methods and it was not a serializable list, then we would get not serializable exception in Java. Oh, and this works because string and date are already serializable types. Many of the built-in types in Java are already serializable themselves, so you don't have to write any special version of string that's serializable. The problem, though, is that the default serialization that we used before can be inefficient, and sometimes it can even be incorrect. So here's an example where I take the same string with 25 characters. I create lists of size 1, 10, 100, 1000, and 10,000. This loop will create those lists and then add things to them and serialize them, seeing what the file size is after each time that it creates a list of a different size. For instance, it serializes the list with one item, and it was 188 bytes. It serializes 10 item list to 287 bytes. So you can see it's growing as the number of items increases. And when we get to 10,000, we actually get a Stack Overflow error. This is because it's having to follow that graph of the references from one cell to another and trying to make 10,000 calls to the serialized methods for each of those cells causes a Stack Overflow. So the built-in serialization is going to be following that set of references recursively and therefore causing Stack Overflow errors when it's going from item to item to item for too big of lists. It's also slow because it needs to be ready to handle very complex graphs with cyclical references and things like that. So you can see the empty list was only 83 bytes. One reference, it was 188, and then 287, then 1,277, then 11,177. So it's growing a fair amount as the number of items in there grow. It's worth noting that every item in that list actually is a reference to the same string. So we could increase the stack size in Java and allow more calls to be made. And then we're actually able to get that 10,000 item list, and it's about 110,000 bytes. So we can't, however, serialize a list of 100,000 even if we gave 2,000 megabytes as our stack size. We still are going to run out of memory and get stack overflows. The file size appears to be 11 times the number of cells plus 177. So it's 11 bytes for each cell and then 177 for the string because they all have a reference to that same string. Java will be somewhat smart about that. If it's the string that it's already stored, it won't necessarily repeat it over and over. It will store its data and then it will store small amounts of reference information. That's where your 11 bytes are coming from, well, some of it at least, times the number of cells. And it has some amount of overhead to store information about what type of object was serialized and some other things like that. If we make sure that it's a new string, not a reference to the same one over and over, so this will be new objects, same data, but new objects, then these are treated as different string objects, and our list's serialized size will grow much more quickly, up to 340,000 in our 10,000 item list. So the file size now appears to be 34 times the number of cells plus 154 for overhead. So you see the overhead is a little lower because we're not storing that string. Now we're having to store the string for every single cell. So the 23 that was taken away as the single string reference that needed to be stored here has now been added to the size of each cell. So it's growing very quickly. However, we can customize our serialization and do it a little more intelligently in a few different ways. For instance, a quick gain that we could get is to not store the tail and not store the size, but to recalculate them when we deserialize. So we still have the head, tail, and size inside of the list itself, but when we serialize, for instance, or when we deserialize, for instance, with our read object method here, so we override the read object method and we say the size will be 0 and the tail will be null at the start, and then I'm going to be increasing size every time I add a new item. And I will start off with my tail equal to my head, and then I will say tail equals tail.next, as I read in a new item all throughout. So this gives us our list size at the end, and our tail will point to the correct thing. It should work just fine to get the whole list in. This is the deserializing part. And similarly, when we're serializing, we can override so that it's not getting not storing the size and the tail at that point. Oh, the reason actually we don't need to override the output, the serializing, because if we use the word transient, then that just tells Java this field doesn't need to be serialized. Either it's not important or I can calculate it as I go. So we only need to override read object. And that way, when we read in a list, we'll just recalculate the size and the tail. Okay, so now we've saved a little bit. The cell size will still be 11 and 34, depending on whether it has one reference or whether it's new strings for each one. So with one item, they're both the same size, but then the one with new string copies, new objects each time, is growing very quickly still. So we saved 28 bytes by not storing the size and the tail. It's a little bit, but not really worth celebrating too much. This can be a big gain for us if the transient fields, the ones that we mark transient and say that they're not going to be serialized, are complex things with a lot more information to them. But then that may also mean that as we deserialize them, we may have to do more calculations or more building to rebuild those things as well. A better approach is to do serialization that's completely independent from how the thing is represented in memory. We don't have to do these storing of cells, for example. We could just store the data that was in the cells and not have to worry about the overhead of whatever, representation is needed for each cell. So, for instance, we go ahead and mark all of our fields transient, because we're just going to store the data manually here, essentially. So what we do is we write the size, and then we call write object for the value in each cell. So our cells were storing strings, for instance, so we're just going to store the string's value. We don't need to store any information about the fact that it even was a cell. And this saves us at least that one reference from the cell to the data. We're just going to store the data directly. And when we read it in, we will give default values to all of those list sort of things like the head and the tail and the size. And then we're going to get the strings, the actual data, the values from our input stream, and we'll add them one at a time until we reach the size. So we'll read in one value at a time, add it to our list, and then stop when we reach what we stored as the size, because the size was the thing that we stored first here. So that saves some overhead, both in the time that it takes to write out our objects, because Java doesn't have to do all of that traversing of graphs and references. We won't get stack overflows because we're not recursively trying to follow those references to each other. And when we read in, we can just read in the size and then each of the objects and grab them and put them into our data structure. Now, the file size of the empty list is 38. The file size with one value is 66, both for the single reference version and the lots of different object copies version. The single reference version only grows up to 50,000, so I think that's about half as much as it was in our previous implementations. And the many different copies, many references version, grows up to 280,000, which I think is about 100,000 less than our previous one that was 340. Yes. A little less than 100,000 gained there, reduction in the storage. So it's 5 bytes to store the shared strings or 28 bytes for the individual strings per value. The 5 bytes is because they're all referring to the same object, so it's just the reference to tell us that that's the object they're referring to, whereas the 28 bytes stores the actual strings data. In general, this will be much smaller and it will be much faster, again, because it's not having to recursively call and follow all those references. I mentioned the version ID before. These are used in programs that have serialization to indicate that there's been a change to the way that the serialization has been done. So if, for instance, you wrote your serializable list using the default Java serialization tools, you might label that as version 1 of your serialization. And later on, if you decided to go back and customize the serialization, you might make that version 2. And if you found an even better way to serialize it, you might make that version 3, and so on. This is what allows your program to stop if someone tries to read in an outdated type of serialized data for your class. So if someone tried to read in a version 42 serial list with code that had been compiled for version 43, then you would get an exception and stop them. Rather than reading in the list and having terrible junk data that may not actually be a valid list, we throw an exception right away and say, your data is outdated. It's not going to work for the current version of the serializable list. It's also worth noting that the default serialization for hash tables in Java is incorrect because when they are deserialized, new objects might have different hash codes. For instance, the built-in hash code method in Java relies on memory addresses, and so the hash code might change from that. This is true in at least some of the versions of Java. This may have been fixed in later versions, but it definitely can be true for built-in serialization, that it may actually be incorrect depending on the way that the serialization is done and what that class relies on. Serialization is a somewhat dangerous thing to do in your code because you are reading in data from a byte stream. It's possible that people may make attacks on your program by trying to alter the byte stream if they're able to see your network traffic or mess with those files and maybe add some data to it that would cause your program to behave badly or even cause your program to execute malicious code. So this is why it's important to write safe serialization and deserialization methods, but that can be hard. In simple situations, the primitive types and strings can be saved efficiently with data output stream and data input stream as well. These are all some of the different little notes, but hopefully the overall idea that you take away is that we can actually store or transmit objects in Java and in many languages by using serialization. In Java, we can use the default serialization by calling to the write object methods that will turn our objects into bytes using those built-in serialization methods that will follow the graph of all references that L makes to other objects. All of the objects that L makes references to must be serializable, like strings are, or like its cell class was originally written to be. However, if we want to be more efficient, we may be able to write our own customized serialization methods where we override write object and read object for our class and try to write out or read in that data in ways that avoid having to do that whole graph of references, those recursive calls to write object for every cell, for instance, in our linked list, and may be able to save on storage by avoiding repeated information like how the tail is sort of redundant information. It's referenced in two different ways. And to avoid storing the internal information, like the fact that our data is stored in cells. We can skip the cell representation and simply store the important data from that cell. So you will get some practice with writing serializable data types that have their own custom read object and write object methods, and store that data efficiently and read it back in efficiently in your programs.